All right. Well, welcome everybody. Thanks for joining us. Whoever's was able to jump on in and got all of our information blasts about this. This is our first of what we are calling a pre-tower with K&M technology. Our vision for this is to kind of have a technical discussion. We're not sure how often we're going to do this, but this is the first one, so it's our first trial. So we'll try to minimize the speed bumps through this episode. So I am Mitch Abahusayn. I am the drilling engineering manager at K&M Technology. Sitting in with me on this episode is one of our senior drilling engineers, Rick Walker.
Hello, how you doing? I'm Rick Walker. I'm a senior drilling engineer at K&M Technology.
Good. All right. So for this episode, we were going to talk about the Marcellus, kind of the topics that we wanted to discuss are how sometimes the problems at surface that you're seeing can be very similar, but when you dig down deeper into them, the root causes are very different. So I guess we'll go to the presentation now. I guess, well, first let me start off by just saying, for those that you don't know who K&M Technology is, we really don't want to make this a salesy kind of pitch, but for people that are not familiar with K&M Technology, we do have to just let you know who is K&M Technology. We're a engineering consulting firm. That's all I'm going to say during this broadcast. So we do problem well reviews. We look at well designs and critique well designs and so on. And if you want to know more about K&M Technology, just follow the links to our website. We have some videos that introduce us, but I don't want this broadcast to be a salesy thing. So that's all I'm going to say about K&M Technology. So you can find out more about us online. But if we're having a technical discussion, I guess you need to be convinced that we actually know what we're doing. So that's why I bring that part up. So what we're going to be talking about the Marcellus in this presentation. So I think a lot of people do know where the Marcellus is, but since this is globally being broadcast, got to let people know where it is. It's in the northeast part of the U.S. It's a lot of gas is produced there, so it's around the Pennsylvania area. We're going to talk about two different operators. Both of them have kind of similar problems. So talking about they have difficult trips, stuck pipe, lost BHA, not being able to get your casing down to bottom. Sometimes and this is not something that is consistent on every well. Sometimes they've had success in the past, but all of a sudden things have changed and they've started to have more problems. Operator 2 or Operator B, similar results. So random results where sometimes they're having success getting casing down, sometimes they're not being able to get their casing down, and there's nothing obvious to point to why some wells are successful and some wells are not. So lots of solution tried, but results are confusing and random. Unclear what is the cause, whether it's hole cleaning practices, mud. Actually, on one of the wells, that's how we got into the project. The mud company are ones that contacted us saying that, listen, it seems like we're in fear of being run off because this operator is having problems with their wells, and they're pointing to the mud being the issue. So can you come in and help us out and try to keep us on the job? So, so let's dig into a little bit more details for operator A right now. So just to show you, these are what the well profiles look like. So it's right around 8,000 foot TVD. They drill with water-based mud to about 7,000 foot. And then at that point, they swap over to synthetic-based mud. The curves are built with a 9-degree build rate, and they use a 2-degree fixed bed motor. After they're done drilling the curve, then they trip out because the lateral would take multiple runs to drill. So usually on the first trip out of the hole, they would run a lower bed motor to drill the lateral. And the land the curve at, it says 8,400 foot TVD on the graph. It's a little bit shallower than 8,000. So it just depends on where you are in the formation, how deep it is. But they're all very similar. So the background, or historically, a lot of the wells in the area are drilled with a 13.8 pound per gallon mud weight. So that's how they would, when they swap over to the oil-based mud, they start off with a 13.8. They would start drilling the curve and kind of observe what was happening. And if they started seeing cavings or something, then they would raise the mud weight. And then at TD or on trips out of hole, they might have problems tripping out of hole. Sometimes while they were drilling, they'd have pack-offs or get stuck and lose BHA, and then the casing runs were problematic also.
Hey, Mitch, I got a question for you here.
Sure.
You're talking about listening to the hole and raising the mud weight right out of the gate here. What's going on with that?
Yeah. So the reason why we highlight that in the background, or as a background point to talk about, is obviously we have it's something that we see an issue with. A lot of people do it. A lot of people start off with a lower mud weight and then react to instability. And the problem with that approach is once you have instability, then that's damage that can't be repaired. You can't go back and fix the wellbore. The wellbore is damaged forever. So it's something that's very common. A lot of people do it where they run lower mud weight and react. But if you have a history of having to raise the mud weight, then you're much better off just starting off with a higher mud weight to start with. So what are we drilling? This is Marcellus. So down in, you can see an outcrop in this picture on the bottom left. So you can see it's very laminated shale. These are some of the cavings that were collected while we were drilling. You can see that they're very tabular and flat. So, and it's very strong. The ROPs are not super high in this area. So these tabular cavings, they're hard. It's a hard formation, but they're very big and tabular. So the laminations themselves are kind of weak, and it's prone to instability. So when you're drilling a shale, there's two mechanisms for instability. There's stress-related instability, and that is if you need a higher mud weight just to keep the hole round, just because of the stresses acting on the wellbore. Another mechanism for instability is bedding plane instability. So when you drill, and we'll get into that in a little bit, where the difference between, or the bedding plane instability, we'll dive into that a little bit deeper. So the question is, especially for the bedding plane instability, a lot of people think that raising the mud weight will make bedding plane stability even worse, because you're injecting fluid into those laminations, and then the rock becomes weaker and starts falling apart. At least it seems to be kind of an industry recognized concept that raising mud weight with bedding plane instability is not great. Um, so here we have a log, a log of the formation, and you can see the formation just above, right around 8100, 8150, where gamma ray really peaks. If you look at a mechanical Earth model, and so the mechanical Earth model is telling you what kind of mud weight you would need to drill a stable wellbore. So in the y-axis here is TVD depth. The x-axis here is mud weight, and I have a couple of different curves on this line. The light gray one is pore pressure. Light gray on the left side is pore pressure. Light gray on the right side is minimum stress. And then the dark gray is breakdown. And these different colored lines are mud weights that are required for stability. Your mouse. Sorry, we're working we're working through some issues here. The the light or the green line is the mud weight that you would need to drill a perfectly round hole. So the hole is perfectly round. There's no damage whatsoever. And then we have different levels of instability, yellow and red. And you can, I don't want to get into it, but we classify it as different levels of risk. So yellow is a medium level of risk, and then of how much instability you have, and red is a higher level of risk. So in this zone right here, where the gamma ray is pretty high, it's the mechanical Earth model is predicting that you need roughly a 15 pound per gallon equivalent mud weight before you have really bad instability. And that's right around the bed boundaries. So I told you I was going to get a little bit into bedding plane instability. So here it is. The bedding plane instability, I guess, forget about the text. Just look at these two graphs on the two pictures on the left. They explain everything really well. This is a piece of rock, and in the top one, we are drilling through that piece of rock perpendicular to the beds, how the beds are laid. And you can see when you drill through that perpendicular to the bedding plane, you can drill a nice round hole with no issues. But if you drill parallel to the bedding plane, now the rocks on the top and bottom of the hole start to get weaker and fall into the hole. So from a drilling standpoint, this is not stress related. It's just the ceiling is falling in. Enlargement, the hole enlargement grows exponentially. So if you look at this graph, what you'll notice is the cavings close to the wellbore are small, and they increase in size as you get further and further away. So you can get really large pieces of rock that are falling in. This will only stop when the pieces of rock are actually bigger than the size of the wellbore. So that gives you an idea of how severe this problem is. This will happen while you're drilling, so it's more associated where stress-related instability you would see in a normally faulted environment. You'd see crunched rock on the side and more angular cavings. That is while you're drilling, that's very forgiving. That the sides of the rock could be falling apart, no big deal. But when you're drilling and you have a bedding plane failure problem, then this is going to happen while you're drilling, and the roof is going to be falling in on you while you're drilling, and it's more likely to cause either pack offs or stuck pipe while you're drilling compared to a standard stress related stability issue. Consequences of instability is poor hole cleaning. So large volumes of cuttings, of cavings. So the large cavings are hard to get out of the hole. Also, when the hole gets enlarged, then your annular velocities reduce through that section, so it makes it much harder to clean out that area. Buckling limiting weight on bit. So when you have, one of the things that affects how much how much weight you can apply before the pipe buckles is your annular clearance. The more confined the pipe is, the more compression you can put the pipe under before it buckles. If you have a lot of annular clearance, then that drives down the amount of weight on bit that you can apply. So if you have an oversized hole, you limit your weight on bit. Obviously, you end up with slow ROP. If you try to put higher weight on bit and then you end up buckling the pipe, then it shows up. It's very similar. It looks like stick slip at surface, because you're rotating pipe that's buckled, and the buckled pipe wants to push in the side of the hole, and it's catching and releasing. So at surface, you end up with very erratic torque. Obviously, all of that will restrict the length of your lateral. Both while you're drilling and when you're running casing. So if you have a buckling issue with your drill pipe, it's also going to result in more problems with buckling with your casing run. Difficulty tripping. Every time you go through gauge and non-gauge hole sizes, then when you go through those transition zones, it tends to cause a place where you're likely to get stuck. And if you're having problems tripping, then it leads to back raming. When you're back raming, it increases your risk of stuck pipe or losing a BHA. So here are three different wells. That we looked at or were involved in. The first well, we started drilling the lateral with 13.8. So this is the trajectory. In the green is the target zone that we're trying to stay in. On the bottom is gamma ray. And at the very bottom is the percent of cavings. So we start off with a 13.8. We're getting like 30% cavings. And as you continue to to drill, we raised the mud weight to 14.3, cavings reduced. We raised it 14.3. We're still seeing 30% cavings, and then eventually get up to 15.2 mud weight. Cavings diminished to a very small percentage until the very end, where we start loading up again, and that's where we call it TD. On the second well, instead of starting off with a 13.8, we start off with 14.7. We still see a lot of cavings. We raise the mud weight to 14.9. Cavings go down. We ended up with a 15 for most of the well. Saw a little bit more cavings when the gamma ray peaked here. Remember, this is the area where we said that we needed a 15 pound for before we had high levels of instability. And right at the end, we have 100, a lot of cavings coming back again. And then the last well, we started right off the bat with a 15. You see a lot less cavings throughout. And until the very end, we see a little bit of cavings. And you can see that the gamma ray was peaking right here, but we don't have gamma ray all the way to TD because of the offset between the gamma ray and the tool.
Hey, Mitch, I got a question about this.
Yeah.
You know, we start at 13.8 and go up to 15.2, and then by the end, we're running 15 pounds per gallon through the whole well, but we're still getting 100% cavings.
Yeah.
How do we fix that?
That's a good question. It's on all three wells. On all three wells, we have we end up with 15 or 15.2, and in all three wells, even though the third well is better than the first two as far as cavings in the beginning, we still end up in a situation where we end up with like 100% cavings at the end, right at TD. So there's a couple of reasons that might be that that might be happening is, one, you see that the gamma ray is going up, and we said that a 15, at least from our mechanical Earth model, we're predicting that a 15 is what is required to keep the hole stable for a high level of risk of instability. So it might even mean that you need a higher mud weight than 15. The other part of that is, so with the laminated shales and with a bedding plane stability situation, it's not. I said earlier on in the presentation that that there's a belief that raising the mud weight makes the situation worse, but it's not. It's not the static mud weight that's a problem. It's your ECD that's a problem. It's the difference between static and dynamic pressures, and you're not doing. Every time your ECD will get higher and higher and higher as you drill the lateral. They're not running MPD in here or any, and even MPD wouldn't even solve the situation of fluctuation in pressure throughout the lateral section. So as you get further and further out in the lateral, the difference between static and dynamic is getting bigger and bigger and bigger. So if you are pressuring up the near wellbore and then you bleed off that pressure when you shut down your pumps, it stands to reason that at some point things are going to start falling back in on you. So if you wanted to solve that, then it would, I mean, if we got to well 3, the operator was very happy with the progress at that point. Now, if they wanted to drill longer laterals, and run casing deeper, then it might need that, at least in this area, because remember, 13.8 is predominantly what people use in the Marcellus. So it's not everywhere in the Marcellus that you're going to need a 15 pound or 15.2 mud. But yeah, if you, in this area, if they wanted to drill longer, it might require some sort of well design change, something to reduce that level of ECD. Maybe a larger annular clearance, smaller drill pipe, maybe MPD, because MPD is not going to solve the issue of ECD rising throughout the lateral, but at least it's going to minimize. You can use MPD to minimize the fluctuations between dynamic and static, so they're not as big. So those were how those 3 wells were drilled. This was the result. So on these graphs, this is measured depth versus hook load. The green line is rotating weight, and then the red lines are different levels of friction while we're pulling out a hole. So this is the first well, this is the second well, and the third well. And you can see that in the first well, repeatedly they pull a little tight, and then they have to back ream through some section. They pull a little tight and then back ream through a section, and then at the bottom of the curve they need to back ream through there also, and eventually they pull out a hole. On the second well, it wasn't quite as bad, but they still had to, at the bottom of the curve, they needed to clean that area out. And remember, that was when we started off with slightly lower mud weight. In the beginning of the of the curve, there was more instability. The third well, where we ran the higher mud weight right from the bat, we had no issues tripping out from TD all the way through. It was following a constant trend line, which is what we're looking for. No problems running the casing. A lot of times people are hesitant to raise the mud weight because they are worried about higher mud weight resulting in lower ROP. This is a curve where it shows measured depth versus ROP and measured depth versus weight on bit. And because on the wells that we ran the higher mud weight, because you eliminate the hole enlargement, you're able to apply more weight on bit without the pipe buckling And if you apply more weight on bit without the pipe buckling, then you can achieve higher ROP. So where we started off, we're right around 100 foot per hour, and now we're at close to 150 foot per hour. This is a graph that shows the green and red are sinusoidal and helical buckling, and this is a snapshot at TD if you were to have a string gauge throughout, well, at 13,000 foot in this case. If you were to have a string gauge where measure tension throughout your string and you were trying to apply weight on bit, how much compression the pipe is under throughout the lateral. And so if you have gauge hole, you can run up to 20,000 weight on bit without any parts of the pipe buckling. If the hole is 1 inch over gauge, and remember with the bedding plane instability, it's not, it could be much bigger than 1 inch over gauge. So just 1 inch over gauge, now you're limited to less than 15,000 pounds. So it's like a 25% reduction in weight on bit when you have this hole enlargement. So some conclusions is the higher mud weight is needed before entering laminated, and dusting up is not a good way to proceed. Increasing instability or increasing mud weight after the instability has occurred is you're just trying to manage the situation at that point, but the hole's already damaged. You're much better off preventing the damage from the very beginning. Any occurrence in instability does require a change in practices. So one single pack off, once you have instability, it makes tripping much more difficult. It might force you to back ream. With back reaming, it significantly affects your risk of getting stuck. And one single pack off could be the kiss of death. I mean, it really could. Things can go downhill a lot faster. And issues attributed to higher mud weight, or like the things that we worry about when we talk about higher mud weight, it's really ECD that we're worried about, not the mud weight itself. So if we aggressively address the ECD issues, then the mud weight is not really a problem anymore.
Well, we talked a lot about mud weight during this, Mitch, and I know on that last slide you said we should increase it at least 1 ppg. How do we know it's not 2 ppg or 3 ppg that we need to increase the mud weight?
That's a good question. A lot of times we don't. So a good starting point is to have a mechanical earth model that's calibrated. That at least gives you an indication. I think what's really important is a lot of times we don't know how high you need to raise your mud weight. And I would say the most important thing is, if you notice here, we went from 13.8 to 15.2. So that's a significant increase in your mud weight. It's not increasing it by 0.1 or 0.2 pounds or 0.3 pounds. And what we see a lot is somebody will say, well, I had a stability issue and I raised the mud weight by a couple of points or 3 points and it really didn't seem to help the situation. Yeah, I mean, sometimes that's the case. Sometimes you need to raise the mud weight by like 1.5 pounds before you see any benefit. And it could be 2 or 3 pounds. We don't know. I would say continue to raise the mud weight until the mud weight actually becomes a problem. And in all of these cases, I believe right now we're up close to 16 pound per gallon on wells that we're drilling right now, trying to address that issue. So that's what I had for Operator A. I'm going to hand it over to Rick to talk about Operator B right now.
Okay, this is the Operator B case study. This is slightly different from Operator A, but it's still in the Marcellus Basin. So we're going to take a look at a couple of wells that we looked at initially for this operator. They were having trouble running the casing down to TD, and they gave us a couple of wells to look at. They gave us the red well, which had a measured depth of 20,897 with a 12,000 foot lateral. That one, the casing did reach TD. We also took a look at the blue well, which had a lateral of almost 14,000, measured depth of 22 and a half, a little over, but the casing didn't make it down to TD, so they were curious as to what was the cause of that. Additionally, they were planning the black well, which this had a lateral of over 20,000 feet, which is the longest well as far as the lateral that they drilled to date, so they wanted to make sure that they could get the casing down. We worked on, after the first two wells, planning that well, and the casing did reach TD on the black well. We'll go over that a little later. The background of Operator B is they were drilling wells about 21,000 foot measured depth with 12,000 to 14,000 foot lateral sections. Some of the wells, the casing would make it to TD, some didn't. It was varying, and they weren't sure why. They were, however, planning longer wells with laterals up to 20,000 feet, as we saw, so they wanted to make sure they had this issue ironed out before they started drilling these. What the objective was is to determine the cause of the casing issues in the earlier wells, and then we were going to plan the well with the record lateral length to ensure success based on the results we found from the earlier issues that they had. In the blue well, this is a hook load chart. On the left is the measured depth as the casing went down, and along the bottom is the surface hook load in kips. They ran a well cleanup cycle before they ran the casing of 5 bottoms up at 150 RPM and 500 gallons per minute. The rotary speed and the flow rate are very adequate for the hole cleaning. Our modeling indicated about 7 bottoms up were required, but that's going to vary depending on how clean the hole is and how slow or fast they've been drilling as they've gone along. These are the friction factors lines you can see added into this graph. The casing will make it down to TD with a friction factor up to 0.30, which is they were going between 0.25 and 0.30 the whole way down. So this casing run did make it down to TD. This is the red well. The casing stopped 1,350 feet short of TD. This is the same type of hook load plot with feet and kips. The washed and reamed the casing at about 20,600. They started to run into issues. At that point, they washed and reamed, which the casing was floated mud over air. So as soon as they washed it, it became filled with mud and the weight went up. The torque maxed out and they stopped. And that's where the casing ended up. Their well cleanup cycle consisted of 2 bottoms up at 50 RPM and 520 gallons per minute. The flow rate is good as far as hole cleaning. It's got adequate annular velocity, but the RPM should be a minimum of 80 RPM in this hole with this size drill pipe. And additionally, we predicted about 8 bottoms up were required, and they only ran 2. So as you can see, the friction factor lines for this casing run, once again at 0.30 you would have got to TD, but since they were running between 0.30 and 0.35, they ran out of hook load, and that's where they ended up stopping.
So at this point, are you, based on the analysis up to this point, are you looking at, what are your thoughts? Whether is it hole wellbore stability, or is it hole cleaning, or what are you, at this point in your analysis, what are you thinking is the root cause?
At this point, it's it could be either or. It's tough to tell. I mean, it looks kind of like, from retrospect, it ends up being hole cleaning, but, it could be a well stability issue as well. You need a little bit more information to determine exactly what the cause is.
But if it was drag, because it looks like it's following a certain drag line, right?
Yeah.
And if it's drag, then why did reaming not help?
Because they were running floating stabilizer or centralizers on the casing. When they reamed it, it didn't split the friction factor. It didn't spread the load across the tangential or the rotary and the tangential. So basically, they were spinning the pipe inside the centralizers, but the centralizers were still the only thing touching the surface. So they were stationary, and there was no decrease in drag due to the spinning.
Okay. All right.
Go to the next one.
Sure.
This is the torque you see. When they started reaming the pipe, the torque climbed relatively quickly because they were washing it as well. The lines you saw initially, those friction factor lines, show that up to about a 0.40, you could have got it down to TD with torque. But
is the casing fully empty, or are they running mud over air?
they were running mud over air initially.
Okay.
So it was okay for torque, but once they started washing it, filled the casing.
So these are the torque lines after filling up the casing.
Yes, the blue and the green are now 0.20 and 0.25 after filling the casing. So you're well above the light blue shaded area is your makeup torque.
Yeah.
So at that point, you can't rotate the casing at all, which they discovered. This is zoomed out of the same graph, so you can see it from now 10,000 feet down to TD. If you notice, the top three friction lines will now go out horizontal, basically. That is buckled. That's where you have the casing buckled, and at that point, it's not going any further once you hit this horizontal point. The other two just aren't going to make it due to torque.
So even if you're trying to ream, which is supposed to reduce drag, but you're so that was because of the flow decentralizers, right?
Yes.
It's not uncommon in the U.S. to run casing with no centralizers on it, because people believe that centralizers hinder your ability to run the casing down, which seems to have actually been the case in this. So was running centralizers a bad idea?
No, in this case, running centralizers wasn't a bad idea. It's important for the cement job to run the centralizers, because once you fill the casing at TD, you won't be able to rotate it during the cement job, so you could suffer with all your cement channeling down the high side. The problem is not running fixed centralizers. Fixed centralizers would have allowed you to rotate the pipe and reduce the drag on it in order to ream it down to TD. This is the black well. This is the one that we were modeling and then they ended up drilling. This one has the 20,000 foot lateral. As you can see on this, floating at mud over air, it's a hybrid casing string, 23 pound over 20 foot. The casing won't run conventionally to TD for anything over 0.25 friction factor. And on the last wells, we were looking at 0.30 to 0.35, and those were shorter lateral holes. So if we go to the next slide, rotating the casing with fixed centralizers, now we can get the casing down to TD at 0.45, which is 0.10 higher than the previous worst case. So with the fixed centralizers, you can rotate the casing down without an issue. You've got plenty of margin for error there.
I think it's also worth noting, so in these wells, they are running a 13.7 mud weight.
Yes.
Yeah. Okay. So let's take a look and see what the final result was.
So here's the final result. What they ended up having to do, or what they ended up doing, is they didn't need to rotate the casing down due to the fact that they did a proper job of hole cleaning. Their friction factor was below 0.25 during the entire run, and the casing made it down to TD without any issue whatsoever.
All right. That's good. I got two questions about the fixed centralizers.
All right.
So one of them is fixed centralizers aren't cheap. So how hard of a sell was it to get them to run fixed centralizers?
It was a very hard sell. They hadn't done it before. They were very skeptical about it. It was something new to them, and the cost was also, like you said, prohibitive. But going through all the possible scenarios, assuming what we've seen on the previous wells, there wasn't any way to ensure that it was going to get down without fixed centralizers. And after going through every different possibility we could think of with them, they finally agreed that that was going to be necessary to get this down.
And through better hole cleaning, we actually ended up with lower friction than we had expected previously, and we didn't need to rotate. We got the casing all the way down without rotation. So, do you regret recommending the fixed centralizers, considering how expensive they are, when we didn't end up needing it?
No, not at all, because we didn't know at that point, based on what we had seen, we were running between 0.3 and 0.35. And just to ensure the safety of getting this operation completed successfully, it was well worth it because the risk was too high not to. If we would have run into some issue somewhere along the line and not been able to rotate, it would have been stuck and it would have been over.
Yeah, I'd agree with that.
Going forward, if you have more data and you can consistently do it, it might be possible to go to a
I think
floated.
Consistently do it is
the key.
Is the key there. I would say even on a second well, I would still run them.
Oh yeah.
Until you had like 2 or 3 or 4,
You've got it where you're down 0.20, 0.15 on a consistent basis on multiple wells, and that's where you're going to end up. Until that point, yeah, I would keep running them because a sample of one well compared to the rest of them isn't enough to get it to stop.
Yeah. Yeah. So that is.
Yeah, the last one is just to show what the actual friction factor was.
Yeah.
You could see it's hovering around 0.20 most of the way, which is due to the fact that they did a more than adequate job of cleaning up. They had about 10 bottoms up at 150 RPM and 625 GPM. So they cleaned the well, and that's what enabled them to have the lower friction factor.
Good. All right. Well, that is the 2 projects that we wanted to share. 2 projects, very similar results, where difficulty tripping, difficulty getting casing down, root causes were very different. The first one, it was all about wellbore stability. The second one, it was just more hole cleaning practices, and I guess you could call it a well design issue. Ideally, if you're expecting to have to rotate your casing down, then ideally, stick fixed centralizers on there. But a lot of times people don't have the appetite for that expenditure. So they'll either not run centralizers at all, which it makes you have to question how much better the cement job and how much better your frac stimulation would be if you did centralize it and get a better cement job. But it is very common for people not to centralize. The other thing you could do is be selective about your centralization. So maybe centralize every 200 foot and then get decent cement plugs at least, isolating between frac stages. So there's a couple different options that you have to, it's all about managing between how much you're willing to spend on it versus the benefit that you're going to get out of it. Obviously, if you don't get your casing down, then there's not a whole lot of benefit there. So that's something that you got to solve.
And you got to look at the length of the lateral as well, because the longer it is, the more complex it's going to be.
Yeah.
And you won't be able to rotate casing strings to help with the cement job when you get in those really long laterals.
So that's all we had for the projects. I guess we have our producer in the back room. I'm guessing he has been monitoring. We don't have, between Rick and I sitting in this room, we don't have access to questions that have been submitted. So I can't see any, but if Chris has any.
Well, thanks a lot, Mitch and Rick. A couple of questions that came in previously were, how do you distinguish between poor hole cleaning and wellbore instability, and what signs should you be looking for?
That's a good question. So between wellbore stability and hole cleaning, like we said, some of the stuff can look similar at surface. So one of them is to look at your shakers, look at what's coming back at the shakers. If it looks like if something comes back across the shakers that doesn't look like it was generated from the bit, then you have a stability issue. The other thing is problems related to instability tend to be more rapid. So like when you're tripping out, if it was a trip out with poor hole cleaning, you usually see that the friction gradually increases as you're pulling your BHA into through some cuttings that you've left down hole, or if you're running your casing down through cuttings, you tend to see that the friction will start lower and it'll gradually get higher and higher and higher as you're going. Where with a stability issue, it's just
You're going to hit a wall.
Yeah, it's almost like hitting a wall. That's one part of it. But in Rick's case, the operator that he was working with noticed that the hole cleaning was bad, but it wasn't so bad that it just meant that they had an average higher friction factor. And that higher friction factor resulted in buckling of the pipe. And when the pipe buckles, then it stands up similar to like you hitting a wall also. So there's a bunch of different factors that go into it.
Okay, thank you for that. Another question that came in was, laterals are getting longer and longer in the U.S. and around the world. What do you think the limits are, and what are we doing to overcome those limits?
That's also a good question. So what we are doing in the U.S. is it's a challenging environment when you're drilling unconventional and you're drilling 10 20,000 foot laterals. As far as like world record wells, they're not in the same classification as say Exxon Sockland wells or some of these close to 50,000 foot wells, but that doesn't make them any less challenging. The stuff that was being done in the Utica with 20,000 foot laterals, I would say the biggest, we have figured out how to drill really long laterals. We figured out at least mechanisms to get really long casing strings down. The bottleneck that I see, and in some cases we say in the Wolf Camp, we have Shell doing, horseshoe wells where we were limited on how long we could drill because of the lease limits. And then that changed where we started combining leases and drilling longer laterals. Even within one lease, now people like Shell are drilling horseshoe wells where they're drilling 5,000 foot out, making a U-turn and drilling back. So it's over a 10,000 foot lateral, but the concept there is to replace two 5,000 foot laterals. How they're doing it. I would say the drilling and getting the casing down are not the main issues going forward. The issues going forward is the stimulation, and more so how do you get these like once you stimulate the well, you end up with a well with a bunch of plugs in it, and how do you get those plugs drilled out? If you're running 5.5 inch casing, then you're stuck with stick pipe like 2 3/8, 2 7/8 stick pipe to clean it out. The torque rating on that is really low. Coil tubing is not going to get down. So, and for a while there was the dissolvable plugs were getting really popular, but based on our conversation with operators, it's kind of how effective they are is there's still work to
optimize
the dissolvable plugs, because the last thing you want to do is put all this money into a well and end up with something with a bunch of plugs in the hole where you can't get them out and get your production on. So I think the completion side is the bottleneck going forward.
Thank you. Another question that we have is, when we are reviewing wells, how can we avoid the traps of knowing what we're reviewing is relevant to wells that we have coming up, and something that is beyond what the understanding of what we're currently reviewing is?
I think so. I think I understand that question. It's like in these two wells are projects that we as in K&M worked on. The well with the instability was the well that we worked on first. And then this, based on the success there, that was why the operator on the second well had gotten wind of what we had done and contacted us. So when we started looking at the second project, I think it is completely natural and
I think it's the same thing.
to think it's the same thing. You know, especially when they're drilling with a 13.8 mud weight, and you see that that's what we did previously. It's like, well, you know,
Yeah.
all you have to do is just raise your mud weight and fix the issue. So I don't think, and honestly, I think it'd be stupid not to go that route because, I mean, you want to get to the answer as fast as possible, right? So if you have a reasonable idea of what you think might be the issue, I think it's completely natural to go down that route to see if there's data there to support your thesis, right?
Yeah.
Or your hypothesis. The problem is if you try to manipulate data to fit the narrative that you want to sell, right? And I think that's where our group is. It's a good environment where you're surrounded by other people. And so when we work on a project and we come up with a solution, before we even sell it to the client, we have to sell it to each other.
Yeah.
And it's not uncommon where we'll sit in a meeting and it's just like, no, that's not passing the sniff test. You need to go back to the drawing board and dig a little bit deeper, you know?
Yeah, and this was a perfect example of that because these wells were drilled with operator B at 13.8. Some of them were good, some of them weren't. So why was that the case if they only did 15.2 or 15.5?
Yeah. I remember those conversations where it's like they needed to raise their mud weight, and Rick was like, "No, I thought so, but I really looked at this, and it doesn't seem like it's a stability issue. It seems like it's more of a well design and just practices issue."
Yeah.
And we fixed it, and the problems went away. So.
All right, perfect. We've got another question that says, at what depth can you confirm that the cavings are coming from?
Oh, that's it. So, if they are laminated, right? If they're laminated tabular cavings, then you know that they are coming because you have to drill those parallel to your bedding plane, for that to happen, right? So the fact that we were getting tabular cavings, we know that they were coming from somewhere in the lateral, close to the lateral, right? If we were having more angular cavings, then it becomes more difficult, whether it's coming from the lateral or if it's something a little bit shallower. But usually, like that, and that's why monitoring the cavings or monitoring the shakers is really important. Because so we're an engineering consulting firm. We also send people to the rig. I've been to the rig a lot. And when I'm at the rig, that's one of anytime I move around the rig, that's someplace that I go is I try to make a pass by the shakers to see what's coming across the shakers. We talk a lot with the shaker hands because when the cavings start coming back, they usually come back pretty close to when you had drilled that formation, especially if you've had a couple of cycles with the pumps off, then you'll start seeing those cavings. It's not common for you to drill a section and then 24 hours later
See cavings from
that section that you drilled 24 hours ago.
It can happen, but it's very, very rare.
Right. And I guess as a last thing, just to give the geologist people a bone, I've seen people where they've actually taken cavings, given it to the geologist for them to look at it under them. I don't know. That's not my expertise at all. I don't know exactly what they do, but they look under a microscope and they try to tell you what age it's from and whatnot, and the depth that it came from.
Okay, we've got one more question, and I believe this pertains to operator A. All three wells were landed into the same formation or layer?
That is correct. Yes. All of it was the same stuff. And you can see, maybe if you want to pull up so operator A, if I go back here, so yeah, it's all the same layer, and you can just see so they're trying to geosteer within that layer, and every time that they try to go out of zone, that's when the gamma ray kind of spikes. So they're trying to stay within that layer. So this is a little bit off topic, but something that I try to argue as much as I can is when you have a one zone, like when on the MEM where we showed that small layer that required a much higher mud weight with that gamma ray spike. Sometimes if that's like the sweet spot where all the good oil is, sometimes we're forced to drill through that even though we're fracking. And again, I'm a drilling guy, I'm not a completions guy, so I'm not going to pretend like I'm a fracking expert. But instead of drilling in a formation that is really difficult, especially if you're going to frack it, why not just drill in an adjacent formation that's a little bit easier to drill with a much bigger mud weight, with the assumption that when you frack it, I mean, those fracks surely are going to, they have some vertical height to them.
Yeah, they're going to propagate.
They're going to propagate. So, but for whatever reason, it seems like, we have to stay in this formation because it's the sweet spot in the zone, even though if you just move 5 foot 10 TVD or 10 foot TVD, the mud weight window is so much bigger and it's so much easier.
Okay. One more question.
Yep.
How can you tell the hole was over gauge? Did you run any logs to measure?
Not in this case. We have done it previously where, I guess when we're looking at this, where we're saying, let's take a look at buckling resistance for a gauge hole versus a 1-inch over gauge hole. Not in this case, we did not. We know that the hole was over gauge because we saw a lot of cavings. Right? You can't have cavings and have a gauge hole. So we know that the hole is enlarged. We don't know how much it's enlarged, so we just guessed in this. In this case, we just guessed that it was 1 inch. We have worked, there's another area, another field where we had been contacted because the off-bottom torque was much higher than their drilling torque didn't make sense. Their drilling torque was really high and it wasn't making sense. So we were contacted to see why was drilling torque so much higher than what they were expecting. And we did some modeling, and because when you have an oversized hole, you end up rotating buckled pipe and the torque was much higher. So they were drilling 6 and an 8-inch hole. And I kept on increasing the size of the hole until I got to 12 inches. And it didn't make any sense to me that you'd have a 6-inch hole grow into 12 inches. But I went back to him and I said, listen, the modeling says that the hole is enlarged. It could be enlarged up to 12 inches. And I'm like, well, I wish you would have gotten back to us like 6 hours ago before we twisted off. So they had twisted off and they pumped a fluid pill to kind of gauge how big the hole was, and it was 12 and a quarter. It was like within a quarter of an inch of what the modeling said it was. And that's one of the parts where it's like, I don't know. I'm an engineer. And that kind of stuff was really cool to me. It was like, wow, we did all this modeling. We put all this effort in modeling, and we were within a quarter of an inch of something that I didn't even think was possible. I didn't think you could have a 6-inch hole that grows to 12 inches without the hole completely collapsing and just packing off.
Or noticing that much coming across
Right.
the shakers.
Right. So the short answer is we don't know how big it was. We didn't run logs. We didn't run a fluid caliper or anything in this well, but we have done that previously. But we know for sure that it was oversized because of the cavings. Okay. So that's 1 hour. This is our first episode. Thank you for those that sat in and joined us for the first episode of Pre-Tower with K&M Technology. Leave a comment, smash the like button. No, I'm just joking.
Follow, share.
Follow, smash that like button. No. If you did, but in all seriousness, if you did enjoy this, if you did find value in it, we're trying to do better. Just being out there and talking about the stuff that we do and just bringing interesting discussions. So if you did find this enjoyable, if you got something out of it, please leave a comment. Let us know some ideas of some topics that you may want us to discuss in the future, and we have some ideas, but
We're willing to listen.
We're willing to listen to. I mean, we're doing this for the community. It's not for us. We're not getting anything out of this. So, all right. Okay, we're done.
Thanks a lot.
Peace. Thank you, guys.